Rachel, who's a professor at the London School of Economics. Okay, so at a high level, today's talk is about when can I trust my data analysis? As we get more data and better computation, increasingly data analyses can drive life-changing decisions. This could be in medical advances, it could be in individual medical care, it could be in cybersecurity, it could be in personal finance or financial policy writ large. And all of these are cases where I really care about getting the outcome of my data analysis right and making good decisions. So I really want to check that I'm doing well at these things. Now, a typical setup that we have when we are analyzing data for the purposes of making these important decisions is that we run some data analysis on some available set of data that we have to reach a decision, and then we apply that decision to new data. Okay, so as an example, we're going to look later at a microcredit study in Mexico. Recall that microcredit represents these small loans to individuals in impoverished areas, and the hope is to help raise them out of poverty. And so if the microcredit study happens in Mexico, well, ultimately we want to know, is microcredit going to help people in another country or elsewhere in Mexico, or even at just a later time in the same place? And an observation that we're going to make today is that we might worry about generalizing the results of our data analysis, the conclusions, if it turned out an extremely small subset of our data was absolutely instrumental to the original analysis. So something we're going to see later on in the talk is that there is a real study of microcredit with 16,500 data points in Mexico. And we find just one data point drives the sign of the effect, that if you drop one data point, that's the difference between microcredit helping people and microcredit hurting people. Now, you might think, wow, that sounds problematic. Maybe the problem is that there's not enough data. And I would say that this is a pretty huge data set by social science standards, which are already much higher than many other areas. I know in ML, we often talk about, humongous data sets, but there are plenty of areas out there with a lot less data. You might be thinking, man, maybe the problem is these ultra modern complex machine learning methods. And no, this is a simple linear model that I'm talking about. You might be thinking, hey, the problem is observational data. No, this is gold standard randomized controlled trial data. And so hopefully I've piqued your interest that you want to know what's going on here. You want to know, in particular, how could we detect if this is going on? And we're going to see that you couldn't just check every tiny data subset. That's just going to be astronomically computationally expensive. And so what we provide is a fast and automated an accurate approximation. Not only do we have theory to support our approximation, but importantly, nobody has to trust our theory because we're going to show that you can check it directly at an extremely small computational cost. Okay, so in the rest of the talk, I'm going to start by talking about what's this dropping data subsets thing? When do we care about this? I'm going to talk about how we would like to drop data subsets if we had infinite computational power, which we do not. And so we'll talk about why is it so computationally expensive to do this thing directly. And so we're going to provide a fast and an automatic approximation. I'll talk about that in some detail. Then we're going to talk about some actual real life and simulated analyses. The simulations will help us get intuition. The real life analyses will show us that this really does happen in real life. We'll see that while some analyses are robust, some pretty important ones are not under this definition of robustness. And we're going to see that non-robustness in the sense I'm talking about today isn't something that's just a product of gross outliers, of large p-values, of heavy tails, as is the case with many other types of robustness that you might care about. Here we're going to see that it's really a product of low signal to noise in the original analysis. Okay, so let's start by talking about when do we care about dropping data subsets. Okay, well, so first of all, let me just make an observation that unfortunately, and I'm sure I'm guilty of this as well, when we talk about sensitivity or robustness, it's often as though they are monoliths, but really it's always shorthand. What we really mean is sensitivity to some change. So any useful data analysis has to be sensitive to some change in the data. If you wouldn't feel very happy with your data analysis if it didn't matter whatever data you had, it always returned the same result. But what we really want to ask is, what are the concerning changes? What types of sensitivity are problematic? And that's going to vary by problem. And so what I want to convince you of here is not that we have some method that's going to, find all the sensitivity that you have anywhere in your data, but rather that there's a certain type of sensitivity that is often concerning, and we have a method that can help you detect it. Okay, so just to be concrete, let's look at economics. Why economics? Well, one, it's hugely influential. It drives major policy decisions that affect all of our lives. Two, man, it is a fantastically reproducible field, which is something we're going to come back to a few times. I mean, oh my gosh, we could all learn a lot from economics, I think. And then three, prosaically, we were lucky enough to collaborate with just a wonderful economics expert. Okay, so let's talk about some cases where we'd be concerned about dropping a small fraction of our data. Let's say, again, we're interested in the effect of microcredit as an example, these small loans to individuals in impoverished areas. Suppose, and this is what really happens basically, we run a randomized controlled trial across villages. And some people get microcredit, some people don't. And then we want to check, are people benefiting when they get microcredit? Well, let's suppose that Jeff Bezos walks into one of our villages. And so now the average business profit of people in villages that receive microcredit is absolutely through the roof, just because Jeff Bezos's business profit is through the roof. Now, conversely, if I were to just take only Jeff Bezos out of my data set, it would not be the case that the average business profit was absolutely through the roof. And while this is a cartoon, you can imagine an intervention that only makes the already very rich way richer and makes the poor a little poorer. And while that would look good on average, that's not what we care about here. We care about, in these examples and many in real life, we want to actually help a wide swath of people, but we're measuring a mean effect when what we really want to say is that many poor people benefit. This point is not specific to means, that we're often, when we're using standard machine learning tools, reporting a convenient proxy rather than the thing that we absolutely care about at the end of the day. Okay, another thing that we had sort of hinted at on that first slide is that our policy population is just almost necessarily different from our analyzed population. In general, we look at studies to decide what to do in different conditions. We hope to learn some underlying truth of what's going on in real life. And so when we study microcredit in Mexico, it's not that we're interested in this particular village at this particular time. We'd like to apply it, our results, to a different village, to a different country, to a different time in the future. And so it's just got to be the case that those people have changed. Can we assume that our conclusions are still good? Well, we might worry if dropping a very small fraction of data would change them. Okay, likewise, small fractions of data often are just already missing from data sets. They're often missing not at random. Certainly when people do a survey, sometimes they can't find people for the survey. Maybe some people refuse to participate, et cetera. We can't assume that these people are missing at random in general. And something that is just absolutely the case is that our models are misspecified. There's no way that we're capturing the rich set of things that are going on in the world with the simple models, or even the very complex models that we're using in practice. Okay, so in all of these cases, hopefully you agree that we might be concerned if dropping a very, very, very small fraction of data changed the substantive conclusions of our analysis. And I want to emphasize that these concerns, while I've tried to illustrate with a couple of examples here, are not specific to economics. Just about in everything that we do when we're running some kind of machine learning or data analysis in general, we're reporting a convenient proxy. We're trying to learn something underlying about science or engineering or social science. So where we apply our ideas is typically different from where we got the data to analyze them in the first place. And models are just always misspecified unless you're in maybe like some very specific area of physics, you know that your model is wrong. Now, I also want to emphasize that even if it doesn't bother you, and this won't always bother you, that you should be upfront about it. So for instance, here's a case where it would not bother you that dropping a very small fraction of data changes your conclusions. Suppose I'm studying a town of size 10,000 and there are 6 car thieves in that town. And then maybe there's another town of size 10,000 and there are 3 car thieves. And there is some treatment or control between these towns, and we want to measure that, and we want to measure the effect. Now, in this case, that's around 0.1% or less of the town's population. It's a super, super tiny fraction. We hope that there aren't too many car thieves in our town. But your audience should also probably be clear that when you're comparing car thieves between the 2 towns, your effective data is really like 6 versus 3. It's not 10,000 versus 10,000. Okay, so at this point, I'm hoping that you agree with me that we care if dropping a super small fraction of our data changes our conclusions, and so it would be nice to detect when this is happening. Okay, so let's start adding a little bit of notation to our discussion. So we're going to call alpha the fraction of the data that we're considering dropping. So because alpha is a fraction, it's between 0 and 1, and we're really thinking of alpha as being very small if we're concerned. Because again, eventually you expect that you can drop some fraction of data that changes your conclusions. It's just concerning when it's very small. Okay, what does it mean to change our conclusions? Well, it's going to depend on the study. Let me just give you some examples of conclusions that people make from data analysis studies. They might look at the sign of some effect, like is microcredit helping? If the sign is positive, is it hurting? If the sign is negative. They might look at the statistical significance of an effect. Does microcredit have a statistically significant effect on, say, business profits of small businesses? Often people are interested in both the sign and the statistical significance. Like maybe I would only invest in microcredit as an intervention if it were both having a positive effect and that was a statistically significant positive effect. And then I'd be pretty worried if I could take my analysis, drop a data point, and change to a significant result of the opposite sign. That would be pretty bad. Okay, so to that end, we're going to define some quantities that we're going to care about in the talk today. The first one we're going to call the maximum influence perturbation. What's the largest possible change that we can get in our analysis by dropping at most 100 alpha% of the data? And so for instance, I might be concerned if dropping like 0.1% of my data, super small fraction of my data, could change, for instance, the sign of the effect. So I could look at the effect size, what's the biggest effect size change I could get by dropping 0.1% of my data, and then I'd be concerned if that changed the sign of the effect. Now, if I were able to identify these problematic, or that this was happening, I'd probably want to look at those data points. Like, what are those data points? Maybe I look in my data set, I see Jeff Bezos was vacationing in my microcredit village, and I go, that's the problem. I see what happened. Let's just take him out. And so we're going to call this the most influential set. What was the data that we dropped to achieve this maximum influence perturbation? Now, another way that we could look at this is what we're going to call a perturbation-inducing proportion. What's the minimum data proportion we could have dropped to achieve a certain change? So suppose we're concerned, we're making our decision about microcredit based on the sign of its effect. Well, we could ask, what's the minimum data proportion that we could drop to achieve that change in sign? And we'll write NA if there is no data proportion that we could drop to achieve that change in sign. Okay, so how could we possibly find the maximum influence perturbation? Well, on the face of it, it looks like this is a really easy problem. Like all you do is you rerun your data analysis every time with every small subset dropped, and you see if you can make this change. So let's talk about why that might be problematic. As we said, we're going to look at a microcredit analysis with over 16,000 data points. So let's suppose that we had 16,000 data points. And let's suppose that we're really concerned if we could drop 0.1% of our data and change our analysis. So here we have the alpha that corresponds to 0.1% of our data. That's not 1%, it's 0.1%. Very, very small fraction of data. Okay, so on the face of it, it looks like we're going to have to run our analysis with every 16,000 choose 16 data points. So, or every 16 data points dropped. So that's going to be 16,000 choose 16 different analyses we need to run. In fact, we kind of want to really run it with every 15 drop, every 14 dropped, and so on. But even if we just say 16,000 choose 16 is how many analyses we have to run, that's 10 to the 53 different analyses. And even if our original data analysis takes 1 second, which if you run any kind of machine learning or data analyses, you know that that might be a little bit optimistic. Even if that original analysis takes just 1 second to run, this check is going to take over 10 to the 46 years to run. This is an example of a case where distributed computing is not going to save us. It doesn't matter if we have all the computing of Google and Amazon, this is still going to be expensive. And this is just a typical run-of-the-mill data analysis problem. We want to do this all the time for tons of times. Okay. So it seems like we have a computational issue that we're going to have to deal with. And what we're going to do is we're going to propose an approximation. Before I tell you what that approximation is, let's see it in action. Oops. So let's look at a motivating example. I told you about this microcredit example. Let's get into it now. So Angelucci et al. 2015, an amazing paper. It's the largest of 7 famous randomized controlled trials of microcredit in the economics literature. It has 16,561 households. It's pretty huge. It's examining the effect of microcredit. I cannot emphasize enough how amazing it is in economics that they just have really fantastic data reproducibility, data analysis reproducibility, and data sharing. And so we were able to reproduce this analysis just exactly. So first, let me tell you the very simple and intuitive model that we're going to look at here. It's just a simple one-dimensional linear regression. So here N indexes each small business. XN tells us whether this small business received microcredit or not. It's an indicator, and that's observed in the randomized controlled trial. YN is this business profit of this nth business. And then theta naught and theta 1 are the parameters here. And so theta naught can be thought of as sort of like, what's the base business profit before microcredit? And theta 1 is the parameter that we really care about here. It's what's the effect of microcredit. If theta 1 is positive, then microcredit's helping. If theta 1 is negative, microcredit's not helping. Now, it turns out you can actually use a much more complex model with a ton more covariates. And my understanding from the economists is that it makes no real difference to the analysis. And so let's stick with one where we have a lot of intuition. Okay, so the result that they find in the original paper, and which we're able to reproduce, is that theta 1/2 is negative 4.55 US dollars purchasing power parity every 2 weeks with a standard error of 5.8. And so now we're going to ask, could we drop a small amount of data and change the results of this analysis? Well, first of all, using our approximation, it takes just 2 seconds to find out the answer to that question, not 10 to the 46 years, as we were saying we would have to do by brute force. As I said, we can remove one household, one small business here, and change the sign from negative to positive. That's the difference between microcredit helping and microcredit hurting. But you might be thinking to yourself, yeah, but it wasn't a statistically significant result to begin with, so am I too concerned about that? Well, we can remove 15 data points. That's still less than 0.1% of all of the data, not 1%, 0.1%. And we can get a statistically significant result of the opposite side. So that's definitely a case where you would make a different decision. Now, as I said, you don't have to trust the theory that we have that supports our approximation, although I do think it's helpful. You, as a user, can just rerun the regression to check directly. We tell you, here are the 15 problematic data points. You can rerun your analysis with those 15 removed. And so at the cost of 2 total data analyses, just 2, not 10 to the 53, just 2 analyses, you know that any non-robustness you find is conclusive, that in fact, it is true that when you drop these data points, you get this change. Now, you might be thinking, yeah, but this wasn't a statistically significant result to begin with, so do I really care that I could change the conclusions? We're going to see an example later where we can go from a statistically significant result, drop a very small portion of data, and get opposite conclusions. And it's also in an extremely important influential economics paper. This is not just an issue of gross outliers, as we're going to see later on. It's not just an issue of heavy tails, that there are secret heavy tails here. We're not using a heavy tailed model. It's not just an issue of reporting means. Something I won't talk about in the talk today, just for time purposes, but I'll mention is in our paper, is that we also show that being Bayesian is not a panacea, that you can be Bayesian and still have these issues of dropping a very small proportion of data and having it change your conclusions. Okay, so at this point, we have used our approximation. It seems like we'd like to understand what is that approximation. Oh, and we're going to see that the issue that this is uncovering is a signal to noise problem. Okay, so we talked about when do we care about dropping data subsets. Hopefully I convinced you. Hopefully you will ask questions if I didn't convince you. Hopefully I convinced you that we do care about dropping a small fraction of data, that we would worry about generalizability if we found that we could drop a very small fraction of data and change our conclusions. We talked about how we'd like to drop them if we had tons of computational power, how unfortunately we do not, and so we need an approximation. And so now we're going to talk about what is that approximation? What does that approximation look like? And then we'll get into some more understanding of it in practice. Okay, so first of all, let's talk about a really generic looking data analysis. Suppose I have a bunch of data. Let's say dn is my nth data point. And the data could, for instance, be a supervised learning problem, and I have a bunch of features xn and labels yn, but it doesn't have to be supervised learning. This could be some other form of data. It could be semi-supervised, it could be unsupervised. That's all fine. Now, a typical setup is that I have some parameters that I'm interested in. We saw theta naught and theta 1 on the other slide about microcredit. I have some unknowns that I'd like to learn about, my parameters theta. And I have some loss that relates my parameters to my data points. Let's call that F. Now, a very typical thing that we'll do in machine learning is we'll sum up the losses over all of our capital N data points, and then we'll fit our parameters by minimizing the loss across all of those data points. And so let's call that theta hat. for that argument. Okay, now tons of stuff fits into this framework. I mean, honestly, well, obviously, anything that you're minimizing a loss, you're maximizing the likelihood, you've got a negative log likelihood. It turns out actually what our approach can handle is much more general than what I've shown here. If you're thinking, hey, sometimes I use a regularizer, that's totally fine, we can handle that. If you're thinking I do map for Bayesian inference, which is essentially using a regularizer in many cases, then that's fine. If you're doing variational inference, that's fine. Actually, if you're doing a multi-step analysis, that's fine. Anything that takes the form of a Z estimator, where basically you're taking a derivative and setting it to 0, is totally fine for what we're about to do. But I'm going to stick to this data analysis because it's pretty general and a little bit easier to understand. Okay, so now, as we saw in that microcredit example, it's not just that I learn some parameters, it's that I now make a decision using those parameters. And it's typically not that I just like take my parameters, which could even be high dimensional, and just immediately make that decision. I summarize them in some way. So an example that we saw when we were looking at the microcredit example was that maybe I'll just pick out one of the parameters that I care about. So my quantity of interest is, let's say I'll take the p parameter and I'll look at theta hat sub p. Or I could be looking at statistical significance, in which case I'm going to take the p parameter plus or minus 2 standard errors. So that could be another way that I make a decision. In general, when we actually make a decision at the end of the day, it's typically we've taken that theta hat vector and summarized it in some meaningful way. And so we're going to call that quantity of interest phi. It doesn't have to be only these examples. These are just 2 illustrative examples. Okay, now everything above this bullet point is like, this is your machine learning course review. Now, starting with this bullet point, we're going to start looking at things in just a little bit of a different way. Let's imagine that we give every data point a weight of size W1 for the first data point, W2 for the second data point, W3 for the third data point. We collected all the weight vector W. And so you can think of our original data problem as giving all of the data points a weight of size 1. So we can express that in an all ones vector, 1 sub capital N. And now suppose I drop a data point, then that's like taking the corresponding weight from 1 to 0. So let's suppose I was dropping the 10th data point. I'm going to take W sub 10 from 1 to 0. If I drop the 10th and the 11th data points, I'm going to take both of those weights from 1 to 0. And so hopefully you agree with me that in general, every dropped data subset corresponds to a different weight vector W. Okay, now how does that affect our data analysis up at the top? Well, you can think of it as taking each of our losses and pre-multiplying it by the weight. If the weight is 1, we're including the loss term for that data point, the corresponding data point. And if the weight is 0, we're getting rid of the loss term for that corresponding data point, which is what we would do if we didn't have that data point. Okay, so now implicitly, theta hat, our argument parameter, is a function of W. It's a function of the weights W. It's a function of what data points we include. That's all we're really saying here. And so phi has to be a function of W. Well, 1, because it's a function of theta hat, which itself is a function of W, but it also could be a function of W in other ways. So for instance, in the standard error. Okay, so this is just a slight rethinking of how we think about loss minimization. But now we're going to make the observation that if we're dropping an extremely small portion of data, we're not changing W that much. We're starting from the all ones vector, and we're just letting a very, very small number of the W elements become 0. And so our observation that we're going to take from that is that probably because we're changing so little of the W vector, we could use a Taylor series approximation in W to get a good approximation of theta hat or phi. And in fact, we're going to take the simplest possible non-trivial Taylor series expansion. We're just going to use a first order Taylor series expansion. Okay, so that's what we're going to see on the next slide. So we still have our generic data analysis, now with this weighting corresponding to which data points we keep and which data points we don't. We have our quantity of interest that we take to make our actual substantive conclusions at the end of the day, like should I invest in microcredit? And we have an example. And now we're going to say, hey, instead of calculating 5W for every single W for every single possible data set, dropping a little bit of data, we're going to use a first order Taylor expansion around the all ones vector. Okay, so let me explain what's going on in this equation. So remember, we wish that we could compute 5W for every single drop data subset, but that would be like 10 to the 53 data analyses that we have to run. That's way too many. So we can't compute the exact conclusions of all those data analyses. We're going to use an approximation instead. This approximation we call phi super lin because it's a linear approximation. It's just this first order Taylor series expansion. And in particular, let's just write out that first order Taylor series expansion. Well, first we have the 0th order term in the Taylor series expansion. That's phi of the all ones vector. This is the original data analysis. We're just running our data analysis. We're coming to our conclusion from our original data analysis on the all ones vector is representing that original data analysis. It's like a sunk cost. You have to run one data analysis. But now, instead of running a whole bunch of other data analyses, we're going to approximate what happens with a first order term in the Taylor series expansion. Essentially, we're multiplying the difference between the weights and the all ones vectors by the derivative of phi with respect to the weights. So this derivative, which we're calling psi here, is right here. If you're familiar with influence scores, this is going to look familiar with influence functions. We're going to call this the influence score of the nth data point. If you're not, don't worry about it. This is still just a first order Taylor expansion evaluated at the all ones vector. Okay, how do we compute this in practice? You know, back in the day, people would have said, oh man, this is something we couldn't do because you'd have to write down all these derivatives and that would be a big pain. And of course, now we can automate all of that. So we, and by we at this point, I mean the authors of the paper, not anybody else, can write a formula for this influence score using the implicit function theorem and the chain rule to get it into a form where we can use automatic differentiation. Now, I think people these days in machine learning are super familiar with automatic differentiation and its potential benefits over numerical or symbolic differentiation. If you're not, or just if you haven't seen this paper, there's this great overview paper by Baden et al. 2018, automatic differentiation in machine learning. Just like everything else, this is a case where we can take advantage of that and be able to deal with general loss functions so long as they have the differentiability to get this derivative. Okay, so the point is, this is something we can automate. This is a calculation we can automate. So you only have to run one data analysis, and then we can use this automation to get the linear approximation in all of the other cases. As I said, we're actually not specific to this minimizing, strict loss framework. We can have priors, we can have regularizers, we can have multi-stage analyses. That's totally fine. Now you might be thinking to yourself, hey, what about higher order Taylor expansions? I mean, can't we only do better with that? Well, there are some cases where we think that that's actually pretty important. We have some early work up on the archive to that effect. But in this particular case, the linearity is actually pretty key because we actually haven't totally solved this problem as of this slide. So right now we've replaced our 10 to the 53 data analyses, which is good, with one data analysis, but we still have to get 10 to the 53 approximations. We don't want to do like 10 to the 53 additions. That's too many. And so we really need to make sure that we're not doing 10 to the 53 anything. And to avoid that, that linearity is going to be key, as we're going to see on the next slide. Okay, so we still have our analysis, we still have this linear approximation. And remember, at the end of the day, what we really care about is what's the biggest change that we can make by dropping a very small fraction of data. And here, without loss of generality, I'm going to just say we're interested in a positive change. We could totally be interested in a negative change too. Okay, well, what we're doing is we're replacing this question of what's the biggest change I can get by dropping a small fraction of data with what's the biggest approximate change I can get by dropping a small fraction of data. What's the biggest change I can get in phi ln minus phi of the all ones vector. Now, this is an easy thing to write out using the formula just right above here. It's like we're just taking phi of the all ones vector and putting it on the other side of that formula. So we're left with the first order term in the Taylor expansion. And this simplifies even further. We're just summing over the cases where wn equals 0, because when wn equals 1, it's the whole term is just 0. So we're just summing over the cases where wn equals 0, that is the cases where we dropped data negative of the influence score. And so this suggests a simple, almost linear time algorithm. And that is the following. First, compute the influence scores for each data point. That is linear time in the number of data points. 2, sort the data points. That's not linear time, but if sort is the bottleneck in your analysis, I would just love to chat. I think that is not super common in the economics field, at the very least. Okay, 3, remove the largest influence score. And now we have the biggest possible change that you can get in the approximation from removing just one data point. And now you can remove the second largest influence point. And we have the biggest change that you can get by removing just 2 data points. Okay, and so this tells us how can we get the maximum influence perturbation? Well, more to the point, how can we get the approximate maximum influence perturbation, what we're going to call an approximate maximum influence perturbation? We keep removing the largest influence scores until we've removed at most 100 alpha% of the data, and we ask what is the change that we got in the approximation. Now, along the way, we could say, what were those data points that we dropped? Let's just remember their data indices. And so that'll tell us the data that we dropped to achieve the approximate maximum influence perturbation. Finally, if we care about this other way of thinking of things, what's the minimum data proportion I need to drop to achieve a certain change? I drop the biggest influence score, I ask, did I achieve that change? And I drop the next biggest influence score and I ask, did I achieve that change? And I keep doing that until I have achieved the change of interest. Like maybe I'm concerned about changing the sign of my effect. Maybe I'm concerned about changing statistical significance. I'll just keep dropping until I get to that point. Okay, so this is the approximation. And now what we're going to do is we're going to spend a moment to develop some intuition about it. And then we're going to see it in practice on a few more real influential data analyses from economics. Okay, so let's start by developing that intuition. And to do that, let's look again at a super simple case. I think that, what's great about linear models is that we have a lot of intuition. We have a lot of ways that we can write things about them, that we can truly understand them. And then what's great is that we can go and use our method in more general cases. Okay, so let's look at a super simple one-dimensional linear model with Gaussian noise. So here we have this one-dimensional feature xn, we have our one-dimensional parameter theta, our one-dimensional response yn. Because we're simulating our data, we're going to simulate from a particular noise model. In this case, we'll have a normal noise model with its own standard deviation, sigma epsilon squared, or sigma epsilon. Again, we have to simulate our data. So we're going to simulate the covariates to have their own standard deviation, again, normal with their own standard deviation, sigma x. And we're simulating our data, so we have to specify theta. So we're going to say theta is -1. Okay, so I said earlier that we're interested in changing some substantive conclusions. So if we're going to see what happens here, we have to say, what does it mean to change our substantive conclusion? We're going to draw 10,000 data points. We're going to act like we have a data set size of 10,000, and we're going to ask, can we flip the sum of theta hat? Maybe we're imagining that we have a conclusion that's based on the sign of theta hat, and we're going to ask, can we flip its sign by dropping a small proportion of data? And I mentioned early on, and now we're going to see that this is the case, that this is going to show us that this metric depends on signal to noise. So what do I mean by signal to noise? Let's go into that now. Now, you can think of signal as sort of the strength of the effect. What are we trying to do? Well, here we're trying to change the sign. So we have to make a change, or let's call it delta, of size theta hat to get from theta hat to 0. Now, noise is what makes this a hard problem. Roughly, how big of a change can you get? Now, if you go into our paper, there's a lot more theory than I'm covering today. We show that our approximate maximum influence perturbation metric breaks down roughly as a shape term times the scale term. The shape term is pretty constant across different problems, and the scale term is an estimate of the scaled asymptotic standard deviation. For the purposes of our intuition building, all you have to know is that it roughly comes out in the end for this particular problem to sigma epsilon over sigma x. Let's talk about why that makes sense for noise. If sigma epsilon is super duper tiny and sigma x is super duper large, then we're going to find, if we generate from this model, we have this perfect textbook line. Like the data looks like it's on this perfect line, like it's super clear what theta is. You know exactly what it is. This is an easy problem. It's like a super, super clear problem. Conversely, suppose sigma epsilon is super humongous and sigma x is super duper tiny, your data looks like a blob. You have no idea what's going on or what theta is. It's a super unclear problem. And so in general, hopefully you have the intuition in the linear case to know that when signal to noise is high, this is a really stable problem. When signal to noise is low, this is a really hard problem. It's really unclear what's going on. And we're going to see that borne out in practice. Okay, so what we're doing here is we're changing signal to noise by changing sigma x and sigma epsilon. So on the horizontal axis, we're increasing sigma x. So we're making this an easier problem as sigma x increases. And the vertical axis, we're changing sigma epsilon. We're making this a harder problem as sigma epsilon increases. And now within every one of these little blocks, we're asking ourselves, how many data points do we have to remove to change the sign in our approximation? And so in this lower area where the signal to noise is very high, we're seeing that there is no proportion of data that we're able to remove to change the sign. When you go to the diagonal, where signal to noise is intermediate, there's some proportion we can remove, but it's still pretty darn high. When you go to the case where signal to noise is very low, where sigma epsilon is large and sigma x is small, then there's a very small proportion of data that we can remove to change the sign of the effect. Okay, and we see the same pattern for changing sign and significance, for changing significance, and so on. Okay, so I want to point out a few things. One, we're seeing that the issue is the signal to noise ratio, that this idea of dropping a very small amount of data is flagging cases where we have low signal to noise. Now, in this particular case, there are other ways that we could have known that. One, I hope that by having this super easy metric, it's also just helping people meet them where they're at and look at these other things, visualize their data, realize that there is some instability here. But also there are plenty of cases that are a lot more complicated than a linear model where we might want to investigate this further, or you can't just draw it because maybe it's not just two-dimensional. Now, we're also seeing some important things are not decisive here. We said we might be concerned about dropping a small amount of data because of model misspecification, but we're not just detecting model misspecification, which would be sort of boring because everything is misspecified. Here we're seeing a case where the model is perfectly specified and we're still having non-robustness in the way that we described. Likewise, we have a case where we're dealing with means. So it's not like means are decisive here because we can both have non-robustness and non-robustness. And I should say, same thing with misspecification. It's perfectly specified, but we can have both non-robustness and robustness. And same thing with heavy tails. This is not a heavy tailed problem, and yet we can still have either robustness or non-robustness. So this is just very different from other types of robustness that people are concerned about. Okay, so let's talk about some real data analyses. So there's this very famous Oregon Medicaid study, which you've probably heard about in the news. And here we're going to see that a small p-value is not decisive. Okay, so Finkelstein et al. 2012 had this amazing Oregon Medicaid study. Again, I cannot rave enough about the fantastic reproducibility. There was a lottery in Oregon, and the winners were able to sign up for Medicaid. And so there was this sort of natural experiment that was happening. And there are various things that the paper looks at. One is the effect of the lottery on health. Now, health could be quantified in a number of different ways. And again, you can look at the original paper for all of the different analyses they do. And in our paper, we reproduce all of those analyses and ask about this dropping a small amount of data question. I'm just going to show one particular one here. One notion of health is after 1 year, what is the number of days of no impaired activity over the past 30 days? Okay, so this is a case where there's a ton of data, over 21,000 data points. These are survey responders, so we might have some questions about missing this not at random. And the original analysis found p less than 0.01 for a positive effect. This is the kind of thing that gets you in the news. It's a very exciting result. But we do find that we can drop 11 data points in this case. That's 0.05% of the data. I want to emphasize this is not 5%. It's not 0.5%. It's 0.05% of the data. It's a very small fraction of the data, and we can change the statistical significance of that result. And so just having a small p-value here is not going to save you from having this, this sensitivity. Now, on the other hand, there's something where, just because I want to show you that this is able to flag something interesting, I've focused on non-robustness. Here, I want to tell you that this doesn't just always flag non-robustness. Absolutely, you can be robust. I mean, we saw that in the simulation experiments, but let me also show you that in real life now. And we're also going to see that removing outliers isn't a panacea. Okay, so now we're looking at Angelucci and DeGiorgi 2009, awesomely reproducible, super cool paper. It looks at two different things. So one is the direct effect of cash transfers for poor households on household consumption. But two, it's also interested in, yes, we typically focus on giving poor households these cash transfers or microcredit and see, how they fare. But you might also ask, hey, if they're non-poor households and they're not directly getting the cash transfers, do they still benefit in a spillover way from the poor households getting the cash transfers? And so these are both pretty interesting questions. Let's look at them separately. First, let's look at the evaluation of poor households. So in this case, there were over 10,000 data points. And we find that this result is pretty robust. We are not finding non-robustness in this case. So in particular, the reason that I have a range of values here is that we test for, can we change the sign of the result? We test for, can we change the significance of the result? We test for, can we change the sign and the significance? In all of these cases, we have to drop 4% or 10% or just a lot of the data to change the analysis. And so, we think eventually you drop enough data, of course, the analysis should change. And in these cases, it seems like it has to be a pretty high proportion of data. So this seems, at least as robust as we can manage. Okay, conversely, let's look at the spillover effect on the non-poor households. So here we have over 4,000 data points. The original analysis actually already got rid of outliers. So it deleted households with consumption greater than 10,000 units. You can think of this as the largest response in a regression. And we find that it's still sensitive, even after the outlier removal, that we can drop 3 data points, that's less than 0.1% of the data, to change the statistical significance. So let me just say really briefly, how could this possibly be? How could I remove outliers and still have, this very high sensitivity? Well, in linear regression, again, we have a lot of intuition and we can write certain formulas down. We can check that the influence score is actually the residual times the leverage. And so you could have a very large residual, but a very small leverage, and therefore have a lower influence score. Whereas if you have maybe a sufficiently large residual and a sufficiently large leverage, you can still have a high influence score without maybe being pruned in an outlier pruning. Okay, so let me just make a few connections before I conclude. So I want to emphasize that these concerns are not specific to econometrics. If anything, I think econometrics is doing particularly well by having such amazing reproducibility. That's like the lower bar. This is like the next bar up. How can we run these analyses and check their generalizability? Well, first we probably need the reproducibility. Also, I want to emphasize that this isn't like some kind of gotcha for econometrics. I mean, the people, as we said, could not have been running these analyses before. That you really need the approximation to even be running this. That if you run it, just without any kind of approximation, if you just run it with brute force, I mean, you can't really do that. Okay, our approximation is local. We're doing this Taylor series expansion, and so it's necessarily complementary to global checks. If you're able to do global check, that's awesome. We've also done some work on local approximations before. I think there are a lot of really cool ideas in this area, although they look at other types of robustness, not the one that we talked about today. This is complementary to other types of robustness. So people often think about Huber robustness, tailored checks. In machine learning, we're often thinking about things like adversarial robustness, which is a term of art and really means a very specific thing, that we're changing our data analysis in a specific way. We're changing our data in a specific way. And I want to say that in science and technology and engineering, yes, sometimes we really care about an adversary coming in and changing our data, but sometimes we don't have an adversary. And yet things can still go wrong in our data analysis without somebody specifically wanting to ruin it. And I think that's what we're trying to get at here, is this more prosaic, how can we trust the generalizability of our analysis? Even if we're doing everything right, can something go wrong? Likewise, if you have robustification procedures for other methods, well, for other types of robustness, that's going to be complementary to what we're talking about here. We come from a growing literature on approximate cross-validation and generally use of influence functions for practical checks. So there's been a lot of really cool work in that area. We've done some work in this area as well. So we started off with approximating cross-validation in an AI Stats 2019 paper. And we've since extended that work to high dimensional problems where you really have a high dimensional covariate space, and also more structured problems. So you'll notice that in the loss function that I showed you today, we're sort of assuming that you essentially have IID data. And so if you want to get beyond that, then you can use ideas from these papers that I've talked about here. I mean, it's basically the usual thing that if you have some additional structure, like a time series or something like that, you hope to like get down to the IID case or have something that you can take advantage of there. All of this comes from really an idea from statistics from the 70s and 80s called the infinitesimal jackknife. You can really trace it back to that work because all great ideas come from maybe previous decades in statistics. But what's really cool is back in the day, you know, people would say, oh, you know, this is a cool idea. I can make proofs about asymptotic normality or things like that with this infinitesimal jackknife idea, but it wasn't considered something practical. And I think this has been a big story of a lot of sort of machine learning and statistics recently, is that cool ideas that existed just couldn't be turned into practical ideas because we didn't have the compute, we didn't have the modern automatic differentiation tools and things like that. Nobody wanted to sit around and write derivatives, and now we have the ability to get past that. And so I think that's driving a lot of advances, and this is no exception. Okay, so today I presented a way to check if there's a very small fraction of data that you can drop to change your substantive conclusions. And so if you're interested in this work, you can check out our preprint up on the archive. And also, so again, I want to emphasize Brian Giordano is my fantastic postdoc. And so you can check out this code, rgiordon is his GitHub username. ZAM influence stands for Z estimator maximum influence. Remember I said that our method really works for general Z estimators. And so you can find readmes and all kinds of information there. There have been a couple of cool blog posts about how you can use our method to flag p-hacking. And so this first one is not from us, it's from an awesome other researcher who just, you know, noticed this cool observation. And then the second one is from, again, my postdoc Brian Giordano, and a follow-up blog post elaborating on this if you're interested. And then finally, I'll just conclude with, again, this idea that we really want to be able to trust the decisions from our data analysis. And I think that there's like a whole ecosystem around doing that. That increasingly we're finding that transparency and reproducibility in artificial intelligence are just really important. That, you know, if we're caring about a medical result, if we're caring about a financial result, we really want to have just even this baseline, I think, of understanding what are the elements that are going into that. And we actually elaborate on this in a recent paper toward a taxonomy of trust for probabilistic machine learning, which I think some of the ideas here even go beyond probabilistic machine learning. But this idea that, you know, there are multiple levels here. So first, you know, we care about just even being able to reproduce the analysis, you know what's there. Today I talked about sort of what I would think is the level beyond that. Once you can reproduce the analysis, how generalizable is it? How can we test for that? And then I think, you know, often we check in our machine learning papers for things like, oh, do I have the theory to support that I'm optimizing this result really well? But what if, you know, what if that thing that I'm optimizing itself has issues? And so I think just thinking more broadly about that can be really helpful. Great, thanks so much for everybody listening today, and I'd be super happy to take any questions.
Well, thank you, Professor Broderick. That was a very enlightening talk. I guess it seems like we do have some questions in the audience, so I guess we can start with Michal.
Yes, I really enjoyed this talk. I actually didn't know much about the subject before, so it was really interesting to learn about it. And I have a few questions. First, like, it looks like the theory in a way is a worst case theory, but not always. Like, as you said, not always. Like, I look at worst case. So, for example, I would very much like to know if you have any intuition what happens if, for example, all the measurements can be missing with equal probability. And then specifically, for example, in your example, when you took like the highest, for example, measurements, so it's kind of reminded me a bit of order statistics when you look at like your top measurements, and then you can say something about them statistically and maybe using concentration inequality.
Great, yeah. So okay, great. Lots of great food for thought here. So the first of all, I guess what I would like to convince you is not so much that there are other types of robustness that one might be interested in, but that we are often interested in this robustness. And so let me come back to my cartoon. You know, suppose I have Jeff Bezos walking into my microcredit villages. I really do care about getting rid of the worst influence function in that case, because that's Jeff Bezos. And I think that, as much as the Jeff Bezos bit is a little bit of a cartoon, this is a real issue in microcredit in general, that you could have the issue that there's a few very rich people who are benefiting a ton from getting microcredit, and then maybe everybody else is either not benefiting or even possibly getting hurt. And so you have this issue that, you'd like to maybe be more directly measuring what you care about, but let's be realistic, people are using linear models in practice. And so in fact, they're measuring like a difference in means. And so if you come from that perspective, then like what we really want to do is we want to find, are there just like these few people, maybe just a few rich people that we can remove? And in that case, if that is the thing that we are interested in, then we don't want to do just some kind of random subsampling. We really want to find like this very small amount that is just joining everything, that is driving everything. Because if we do random subsampling, there's a decent chance we're not going to get Jeff Bezos, or we're not going to get these rich people and remove them appropriately. And so I totally agree with you that there is some notion of like this. This is definitely, we are looking at the worst case removal of data points. But I want to suggest that that is actually a super meaningful case, and not in like weird cases. And in fact, this is also what drives our ability to detect things like p-hacking, that it's really because we're getting at these worst case analyses that we can do that. So hopefully just a little motivation about like why we care about that. And then on the issue of like doing statistical analyses of these, one thing I'll just use this as an excuse to point out is that two things. So one, a lot of classical statistical analyses are, pretty much the whole like classical statistical analysis framework is built around this idea of that you have your data is samples from a population. And the reality, and I think what we're trying to get at here, is that that population is not static when we care about generalizability. We just know that that's the case. You look at the population of Massachusetts now and 5 years ago, and it is just slightly different in ways that could be substantive to some kind of intervention that we're interested in, or might not be. And that's kind of why we really want to look at these things, is that notion that the population truly isn't static and is changing. And so I think if we do statistical analyses of these cases, we have to be really careful that we're not just working within this sort of classical framework, because that could lead us astray. So something, for instance, that comes up is that if you're using, and part of the reason that we're able to detect things that a p-value doesn't, is that if you're using a traditional p-value, that it is just the case necessarily that as you get more and more data, your p-value goes to zero. It doesn't matter that maybe there's something fundamentally wrong with your analysis, maybe there's actually something that you want to detect that it's not quite detecting, your p-value is just going to go to zero no matter what. And that's not the case for our AMIP metric. And so that's something that's just very substantively different here, that it's not just doing this sort of asymptotic thing in this one population that a p-value is, in this one assumed null population, that it's actually able to detect that there could be this generalizability issue. So anyway, hopefully that addresses some of the questions.
Yeah, great, thank you.
Thank you.
And next we have Professor Brandon Stewart.
Hi, thank you so much for the talk. This is really great. I love the work, and I love that you guys release software that's super easy to work with. I was wondering, you mentioned very briefly some of the sort of work from the 70s and statistics, and I was wondering if you could talk a little bit about the connection between what you all are doing and DF betas or Cook's distance, or these kind of classical regression diagnostics, and if the right way to think about it is that they're generalizing to Z estimators from just linear regression, or if they're doing something quite different. And I think the big thing that's I'm just trying to wrap my head around is that those diagnostics have a known problem that if you have two data points that are outliers in the same way, the DF beta will, or influence points in the same way, right? The DF beta will sort of underestimate how much removing one of them will do, because it's sort of the other one is still there. And it feels like your metric would have the same issue because of the linearization and the Taylor series approximation, but I might be thinking about that wrong.
Yeah, no, you're totally right about, so the easiest thing for me to address in this question is what are the limitations, and the limitations are exactly what you've described. And so you can imagine a situation where you have some constellation of data points, and they have only influence because they interact in some way. And so precisely because we're doing a linear approximation, we are just never going to capture that. And so if you have that situation, then for sure you're missing out on this. So why do I still have hope? Well, one is perfectly prosaic, is that we've run this on a variety of real data analyses now, and at least in those, we can check, again, as I described, hey, we leave out these data points. Any non-robustness we found is conclusive. It is not the case that there couldn't be more non-robustness. It could be more. But in the cases that we found, we were able to check that at least by removing the data points, that we were able to match our approximation matched what happened when we actually removed them. So that's not to say that there wasn't some constellation that we were missing, but in this case, by getting rid of those, we were able to check that. And I also have hope because we can do this in general. And so when we run an analysis, that means that we can tell you those data points and then you can check removing them. I think so I would say that's one concern. And I'm not, to be perfectly honest, I'm not like totally sure how much that concern comes up in real life. I mean, like just genuinely, it might come up all the time or it might not. At least in our cases here, it seemed like it wasn't such a big concern. I would say the other big concern, which is maybe more oriented towards like a machine learning audience, is that you have this local approximation. And so for instance, if you're working in something like a, deep learning neural net landscape, then, fundamentally all we're going to be doing is say something very local about where you particularly ended up. Again, non-robustness is conclusive, but here I would hesitate to say like that, if we found robustness, that we've really found something. It seems totally likely that there could be something else in that landscape that we're missing out on. And so I co-opted your question a little bit to say more like pitfalls to be aware of, but I think your pitfall was right on. In terms of all these like classic like statistical methods and estimators and things like that, I don't know if I have like too much to say beyond that comparison, like off the top of my head, but hopefully that's already helpful.
Yeah, thank you so much.
Yeah, so I actually also have a question of my own. So maybe this also relates with Michal's question on like how this compares with p-values, in that it seems to me that it's not necessarily that. So like, for example, this is like a worst case approximation, but the p-value, I guess, usually is standardly interpreted as saying, well, what is the possibility that that just another different random sample from the same distribution would give me a different result. And so it seems to me that if we do a worst case analysis like you did, the relation to the p-value should be asking like, actually, how unlikely is it that a perturbation of that size will give us the non-robustness? So maybe like minimum 11 data points out of 16,000 gave me the change in sign, but actually that's only one or two of among like 16,000 choose 11 of all possible small perturbations that can give me the sign change, but all of the others don't. And so, so I guess my question is, do you think that this is just a better metric than the p-value, or that it gives it just more useful? Or, and also about the asymptotics, like when you mentioned that when if you sampled enough, your p-value will always go to 0. But I think you just mentioned back there that this particular metric will not. So I guess, so probably you can do some like a rigorous, like maybe for a linear model, you can just analyze asymptotically what is the ratio of the smallest perturbation to the total sample size. That will give me a sign change depending on, say, the signal to noise ratio.
Yeah, I guess I would say that from my perspective, I think what's actually really compelling about this for me is the first principles perspective. First of all, what's interpretable to a practitioner, and two, what do I really care about? And so I feel like there is some element of many people do not really understand what a p-value is. And even those who do perhaps misuse it quite often. You look back at like the original like Neyman Pearson and like Fisher developments, and it was meant to be this idea of like, oh, I run this, I get this p-value, and then it's something that I think about as I'm doing the rest of my analysis, but it certainly wasn't meant to be the rubber stamp that it is now. And if anything, I think both Fisher and Neyman and Pearson like argued specifically against that. And so there's some element of, maybe if we get back to our roots and we think about p-values in like the right way, that will helping things. But I think that, again, like just coming from first principles, the whole idea of a p-value, as you pointed out, is that I'm talking about like what happens under a null. And I think that something that we want to be aware of in many cases is that we don't have this like single population that we're dealing with in real life. That we're not just making draws from a population and then analyzing that, and then we're going to make draws from that same population going forward. Then we know that things are fundamentally changing. And so I think there's this broader set of questions about how can we deal with that. Now, in terms of, so I made this point about p-values. I'd like to think that even if you don't have a particularly formal data analysis background, that if somebody tells you that you can drop less than 0.1% of your data and you can change your analysis, like change the substantive conclusions of your analysis, that there's just some intuition involved with that. That's like, okay, that's an understandable metric. I know that like seems problematic, that I know what it means to drop data points. I know what my substantive conclusions are. And so hopefully our hope is to be getting more at like this fundamental question that we're interested in, that doesn't depend on having this this overarching population, like this underlying like true population that we're making an analysis from. And so like getting away from even those first principles assumptions that are going in. And so yeah, then we can think about, okay, you know, maybe what's the best thing to do under various cases. But I think a lot of times when we come down to it, we say like, oh, we're going to do the statistical analysis to say that like this method is better than this method. It often is going to rely specifically on making this population assumption. And so like, what's the best way to be thinking about that? I don't know. I guess I just want to at least prompt us to like think about whether we could step away from that.
I see. So basically, if we had a fixed population, then maybe it's still the case that, okay, maybe even if a small amount of data points will change the example, but maybe if we still have something with a fixed population, we can maybe still argue that just that very specific change to give us the maximum deviation is actually very unlikely. But what you're arguing is that the existence of such a small deviation just is an argument against sometimes just doing away with the assumption that we just have a fixed population.
Yeah. Or well, I mean, I guess I would hope that like we could all recognize upon reflection that like we don't have that fixed population, and then how can we address that and deal with that? Because yeah, if we do truly have exactly like this one fixed population, we're making analysis about it, then I think that does say like, hey, all of the statistical tools that are built on that, like those are, you know, perfectly valid tools. That assumption is valid, but I think we know from first principles that like that assumption cannot be true in many cases, and so how do we deal with that?
I think that maybe there are like two complementing questions. The first is like, what is the smallest population that I must change to have like an opposite answer or opposite hypothesis? But then the next question that I think maybe we implied it is like how likely the change will be. Right? Like there will be like, you have to change at least like 0.1 of the population to have a change of outcome. But then like the next question is like, as people from statistics, some of us is like, so how likely is it to happen?
Yeah. This reminds me a lot of you know how a lot of times when we do like statistics or machine learning, we tend to analyze, like if we're doing a supervised learning problem, we tend to analyze y given x, because like while we could model x, we typically don't have a great model for it, and it's nice if we can avoid that. And so I think it's the same thing here, that like we could definitely talk about things like, how is this population going to change and what do we know about it? And I think the reality is that's like an incredibly difficult question. Like what is the population of Massachusetts going to be like in 5 years? What is the population of New Jersey going to be like in 5 years? And how is it going to be different? And I think there are ways that we can try to address that. So like, for instance, like capturing a ton of data as our features, and then trying to adjust under those features. But I also want to suggest that in many cases, we don't either track that data or track enough data to be able to say something substantive about it. And so certainly, you know, if we're thinking about like questions again, like microcredit or healthcare or things like that, we'd ideally, I think that we would feel a lot safer if we had analyses that were really robust to changing populations, to all of these concerns. You know, if it is the case that my analysis can be changed by dropping a small amount of data, and my whole analysis is based on surveys where we know that there's some non-response bias, then like, at the very least, I would suggest that in these cases, we should be concerned and try to look more carefully at what's going on, that we should have a little bit of a moment to think about that. Let me also maybe just take this moment to draw something. So I think that there is a whiteboard option. Yeah. So, when we actually look, I was talking about earlier this issue of these linear models that end up being non-robust. And so we actually look at, the case where, remember, sigma epsilon is very small and sigma x is very large. Well, that data looks like, hopefully you can see my little dots. That data looks like this. Like there's this perfect line, and my little dots of data are just like right around it, And so this is a case where we find that, yeah, you could drop some data, but it's not going to change the analysis. Like there's definitely a relationship between these data points, in particular between the x's and y's. And the case where sigma epsilon is really big and sigma x is really large, it's just this blob of data. And so what we find here, there's a way to, it's a little bit bigger. Oh yeah, here we go. So just this blob of data. And remember, we're trying to get theta, like this relationship between our x's and the y's. And what we find here is that we can drop a very small proportion of data and change the sign or the significance or the sign and significance. And let me just emphasize, like, what is it that we're dropping? Like, for instance, if I wanted to make this a negative result, I'm just dropping like these ones in the corners. And I think that all this is reflecting is that fundamentally there isn't anything going on in this data. And I think this is totally prosaic. If you were to plot your data, you would see this. But at the end of the day, when people just report a p-value or they just say, hey, I found this thing, well, that p-value could just be because I got this blob of data and I got so much of this data. I really know that this blob is very slightly in one direction. And should we base policy on that? Like, should we be, making really big decisions on the blob versus on, these cases where we have like a much clearer notion of, what's really going on in our data? I mean, I think in some sense, this isn't necessarily showing anything like totally new. It's just giving us a tool to detect when these issues are going on.
Okay, thank you very much.
Yeah, so I guess that will be the end of our first talk in our seminaries. Thank you again, Professor Broderick, for coming and giving us this very interesting lecture. And yeah, everybody who's still here, please stay tuned for more announcements for us of upcoming talks. All right, thank you for coming.
Thanks so much. Thanks for all the questions. Really appreciate it.
Yeah, it was great.
Yeah.
Awesome.
Okay, bye.
Bye.
Bye.